Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Think about the last time you struggled to conjugate an irregular verb. In English, we have go and went, is and was. These linguistic quirks feel like unnecessary obstacles, remnants of a complex past that make the language harder to learn. But in the world of physics, these irregularities represent something profound. They are the low-entropy states of human communication. Today, we are exploring a startling intersection between philology and physics, asking a question that sounds like science fiction. Do languages follow the second law of thermodynamics? To understand this, we first need to look at what entropy actually is. In a closed system, entropy is a measure of disorder. The second law of thermodynamics states that the total entropy of an isolated system can never decrease over time. It can only remain constant or increase. In other words, systems naturally move from a state of order and high energy to a state of randomness and equilibrium. A hot cup of coffee loses its heat to the room until everything is the same temperature. This is the heat death of a system. Linguists have begun to notice that languages behave in a remarkably similar way. A vibrant, living language is like a high-energy system. It is filled with complex structures, irregular verbs, unique case endings, and specific tonal shifts that convey deep layers of meaning. These structures require social energy to maintain. As long as a large, interconnected community speaks the language, they put in the work to pass down these complex, high-energy irregularities to the next generation. However, when a language begins to die, when the number of speakers dwindles or the social pressure to maintain its complexity fades, linguistic entropy begins to climb. The first thing to go? The irregular verbs. In linguistics, this process is called regularization. Consider the verb to be. In almost every language, the most frequently used verbs are the most irregular. They are the sturdy anchors of the system. But in dying languages, these anchors start to rust. The complex, distinct shapes of irregular verbs begin to smooth out. They become regular, following the simplest possible path. The energy required to remember a unique past tense form is too high for a system that is breaking down. The language is moving toward a state of linguistic equilibrium, or maximum disorder, where every word follows the same flat, predictable rule. This isn't just a metaphor. Information theory, pioneered by Claude Shannon, allows us to calculate the Shannon entropy of a language. Shannon entropy measures the unpredictability of a message. If a language is highly complex and full of specific, varied structures, its entropy, in the sense of information density, is actually quite balanced. But as a language decays and its structures simplify, the disorder of the system increases because the distinct, informative signals are replaced by noise or generic patterns. When a language follows the path of the second law, it undergoes a process of erosion. Just as a mountain is weathered down into a flat plain by the relentless increase of entropy, a language's grammatical landscape is flattened. We see this in the loss of grammatical cases. Languages like ancient Greek or Latin had complex systems of noun endings that told you exactly what role a word played in a sentence. Over time, as these languages evolved or faded, those endings were weathered away, replaced by simple word order. The high-energy, ordered structure of the case system dissipated into the environment. Why does this happen? The answer lies in the economy of the human brain. Maintaining a low-entropy language requires constant work, education, storytelling, and frequent use. When the social bond that fuels this work weakens, the system naturally seeks a lower energy state. Complexity is expensive. Simplicity is cheap. The heat death of a language occurs when it no longer has the internal energy to maintain its unique distinctions, eventually becoming a pigeon, then a series of loanwords, and finally, silence. This perspective changes how we view language preservation. We aren't just saving words, we are fighting against the cosmic tide of entropy. Every irregular verb we preserve and every complex grammatical rule we teach is an act of defiance against the natural tendency of the universe to turn information into noise. The entropy of verbs tells us that culture, like life itself, is a temporary pocket of order in a universe that is slowly cooling down. By studying how languages die, we aren't just learning about history, we are seeing the laws of physics written in the very way we speak. For more incredible facts like this, don't forget to subscribe and turn on notifications.